Hello, my dear students. Warm welcome to all of you. We are with physics now. Okay, we'll be talking very seriously about physics now. Okay, myself is Dr. Shobboshachi Shen. I'll be offering you the physics courses, course objective, course outcome. You can see on the screen, and we are in outcome-based education. So every course is mapped with what is its probable outcomes, which I have illustrated later on. Now there are 5 modules. Now we'll be adapting one by one to each module and explore the world of physics. Now let us explore what is the topic of the day. You should keep one thing in mind, that whatever we teach in these classes, each video lecture is basically a building block of your future engineering courses. Each class is going to give you some fundamentals, some new concept. And if you add all those concepts at the end of the semester, you will get the correct path of entering into your own engineering curriculum, because all your curriculum are essentially the application of physics. Engineering means physics applications. So let us explore it a bit more. Hello students, very good morning and welcome to class 8 of my quantum mechanics, of my physics 1 courses I should say. There are 36 classes altogether covering so many topics, and we started our journey with the microscopic world, the world of quantum physics. In first year we are learning the theoretical part of it. We are learning some experiments which were carried out between 1900 to 1927. So what I promised you is that each experiment is going to give you some new lesson. Each experiment is going to give you some new understanding, and all those understanding, all those lessons, we should keep with us for the next 1 year or so, so that in the next year we can apply them in the solution of some actual physical problem. So quantum physics is a physics of microscopic world. Quantum physics is a physics of uncanny world. Quantum physics, everything is new. So those newer aspects we try to explore, or we are actually exploring now in first year classes. So the situation is like this much. Let me give you a reminder. Obviously, I don't want to remind myself. Okay, you look at the phone numbers every day I mention. Okay, to get in touch with me, and he is Planck. Okay, Max Planck. So Max Planck, as you can see, he is a pioneer, the father of quantum ideas. Understand? He explained black body radiation. The In the experiment of black body radiation, what happened? The black body was heated, radiation was emitted, emitted radiation was plotted, because corresponding energy was measured by, for each and every wavelength, energy was measured and plotted, and a graph like that was obtained. It was expected that the area under this graph is going to give us the total energy emitted by the black body due to the black body radiation, or due to the heating of the cavity from a temperature T1 to T2 according to our drawing. So now that in order to do that, our job was to perform this integration. I mention all these steps. Today I can say you, we can only do that, you know this, if you know the value of E lambda, the functional form of E lambda. There were so many attempts, and the correct attempt or correct expression of E lambda was given by Max Planck. Now Planck, while doing that, he made a small assumption. The third, actually Planck made an assumption. The assumption 3 of Planck is the breakthrough in the science, breakthrough in the history of physics. He thought that energy of an oscillator, like the pendulum oscillating, should not follow the classical harmonic oscillator formula. In the model, earlier religions also thought that the atoms, which makes the cavity of the black body, because ultimately they are explaining black body radiation, they are the atoms are like oscillator, charged oscillator. Planck followed that same idea, but contradicted religions in the expression of the energy, that he thought that energy would be discrete. So he's the first person who is thinking about this concept that energy may be discrete. Later on, this idea of Planck was further verified through the experiment of photoelectric effect and Compton effect. Now, both these experiments was done after 1900. Okay, that is the in the regime of modern physics, as you can see. After Planck actually with his wonderful idea, quantum ideas. Okay, it is thought that the new or modern physics is born that begins with 1900 with the Planck's quantum concept. So physics or physical phenomena, you can see there is a drastic change in the observation of the physical phenomena. If you look at the situation, many experiments that you have to learn after 1900. What is the change in phenomena? I reminded you the physics you know from your earlier life, that is a classical physics. Classical physics tells you there may be two types of objects in nature. One of them are matter, another are like waves. I mentioned matters have got mass, momentum, etc. Waves have got size, wavelength, frequency, phase, etc. The best exhibition of the material nature is obviously the super collision, and the best exhibition of the wave nature, you can see collision is the best exhibition of material nature, and best exhibition of the wave nature is obviously superposition, and there is a mixed case also. Wave on a matter makes scattering. Okay, scattering takes place. Scattering phenomena take place. Normal reflection, refraction, and the scattering. Now these are classical concepts. So the point is that the moment you cross 1900 and try to explain some physical phenomena with this old knowledge, you will face some problem. Those two experiments are included in our course, the photoelectric effect and Compton effect. Now, both the experiments are actually breakthrough in physics. Okay, photoelectricity, because Einstein got a Nobel Prize because of the explanation of photoelectricity. H. Compton explained Compton effect. That is also the same line of thinking. Okay, what is that thinking? That I shared with you also, that I explained actually how both of them are experiments. So how do you explain the observation of the experiment? Photoelectricity experiment and most of you know, actually all of you know from school level courses. So how it changes? This is photoelectricity, like that some radiation incident on a metal, and photoelectricity is done with usually visible light and with the metallic surface. So basically it is the incident on a metal, but if the wavelength is below some frequency or some wavelength range or frequencies above some frequency, electrons do emit. So initially we thought it's a wave on a matter, so it's a scattering phenomenon that is taking place. But unlike to normal scattering means like reflection, but unlike to normal scattering, what we observe that instead of reflected beam or instead of scattered radiation, we are getting electron emission. This was peculiar. This was uncanny. Because classical physics tells us that you should get a reflected beam, scattered beam, but practically in the experiment you are not getting it. So your classical physics was not good enough to explain the emission of electron. And Einstein explained it with photon concept. He thought from radiation, okay, actually energy is not coming continuously, energy is coming discretely. Each discrete energy value is called photon energy. This is called packet of energy. Just like that, the yellow one is a photon, and at a given time one electron can absorb only one photon. You see the picture, same story. And if the energy is absorbed is sufficient, electron will overcome the Coulomb barrier of the nucleus of that particular atom and ultimately go out. So ultimately, this was the idea of Einstein. He defined photon. He thought that just like Planck thought energy could be discrete, Einstein thought that energy of light or electromagnetic radiation, as a matter of fact, is incident on a matter means you are sending energy, and you are not sending energy continuously, you are making incidents of energy discretely. Each discrete energy packet is called quantum of energy, and with that the emission process of electron was explained. This famous equation of Einstein, the photoelectric equation of Einstein was obtained. So all those things are done. Okay, so much of success story. So now my point is that, again, to reiterate the same story, is you get the information of from the experiment of photoelectric effect.
What this experiment is telling you, this experiment is telling you that at least we have got one experiment in nature where you are not thinking light as a wave, electromagnetic radiation as a wave. You are thinking it is as a stream of photons. What photons are doing? They are making collision with electron. Later on, actually, I have shown you also in Compton effect experiment, photonic mass, photonic momentum. Photons are making collision with electron. You know, mass, momentum, collision are those material properties. So we have been explaining everything as a material property. Okay. So it's a huge departure from classical concept that you are thinking a wave, normal radiation is showing the property of matter. And actually, this was further established through this Compton effect experiment. Whatever I told you, waves can be metal-like. Now, what Compton effect experiment we have done actually, just to remind you, in Compton effect, we used X-ray. So instead of visible light, you are using X-ray, and instead of metals, it was incident on carbon atom. So today we'll try to explore why you are using carbon atom, why you are not using any metal or any other atom, and also why you are using X-ray. So these two questions we'll answer. So X-ray is an electromagnetic ray. Only difference is that its wavelength is too small. X-ray's wavelength is too small a wavelength. So basically, the experiment was like this much. You see that blue one is the incident X-ray. X-ray was incident on one of the electron of the carbon atom. So initially, we thought it is like a scattering process, as you can see in the right side of the picture. So we should get a scattered beam. Okay, just like that. Some red light is incident on a surface, we should get a scattered beam. So if this is the uh, incident ray, and if this is a scattered ray, so if this wavelength is lambda, the scattered beam wavelength is also same lambda. Same story here also, radiation is coming in incident on the electron of carbon atom, and after that we get a scattered beam also. Wavelength of the initial, but the difference is that I ask you in that day to mention what do you see, what is the funnier thing if you compare both the scattering process. Right hand side is a normal scattering reflection, and left hand side is a Compton scattering. Observation was very simple that in the if I compare both the picture, in the right hand side I do not see any change in the wavelength. Incident beam and scattered beam have got same wavelength, which is our daily life experience also. If you send blue light on the wall, reflected color does not become red. Okay, color does not change. But the majority main problem of Compton effect study is that change in wavelength. You see, I use different color here. This is the incident X-ray. It is an incident X-ray. Wavelength is lambda I as I marked here, and this is a scattered X-ray. The wavelength is marked as lambda F. And what is happening? Theory tells me usually red has got higher wavelength than blue. So according to the experiment, the wavelength of the scattered beam would be higher than the wavelength of the incident. So this was the observation. At that time, it's always a peculiar way of thinking that why wavelength is changing, because in normal daily life process of reflection, if I send yellow light on the wall, reflected color is yellow. Red light on the wall, reflected color is always red. It does not change color, or color means lambda. X-ray obviously does not have a color. Okay, that means the magnitude of wavelength actually changes. Actually, it is growing up. You can see there. Okay, so this is a very peculiar observation. Okay, now another in general, actually, what was happening is this one, that apart from that few parallel beams are there also. The one which is facing the electron, it is having change in lambda, and the one which is not facing the electron moves undeviated. So basically, to the left of that orange line, you get X-rays of same lambda, but to the right of the orange line, you get two kinds of X-ray. The one with modified one is represented by lambda F in the drawing, and the one with unmodified line represented by lambda I in the drawing. So I discussed the issue that day also. Now what Compton did, he tried to explain the phenomena. Now this is what he observed. Okay, if the first picture is no change in lambda, second picture you see you are getting the unmodified one. That is the one which because of The blue one according to this drawing, and all of them are lambda I, and lambda f is marked in red. So the idea is that you can see wavelength will be changing. As you can see in the animation also, yellow one hitting the blue ball of the electron is getting shifted and it is going away. Very simple experiment. So I defined Compton effect in front of you like last day. It's a process of it's a scattering process by which the after scattering you get two kinds of X-ray. Okay, one is the modified wavelength and the other one with unmodified wavelength. Okay. So what Compton did, it's an observation of experiment. It's a peculiar observation, but we will have to explain it. Why wavelength is not is changing? Because in normal experiment of daily life experiments, we do not see any change in wavelength. Compton actually calculated, as I mentioned, this change in lambda. He estimated this change in wavelength. Okay, how did he do it? He made two assumptions, which I told you. That incident X-ray in 1923 is doing it. By that time, Einstein has got a Nobel Prize for the photon concept. So basically, the photonic concept was there. So incident X-ray is a stream of photons. Okay, and important idea is that the photons which are making incident on the atomic electron. Okay, there is a collision. You see, photons are like matter. Okay, we calculated the photonic mass, which is like h nu by c square, photonic moment, everything I have done last day. Photonic mass, photonic momentum. You can see h nu by c square is the photonic mass, which is almost insignificant, and photonic momentum is h nu by c. Okay, you can see in this picture. So basically, mass photon is therefore is like a matter because I'm defining photon with some mass, although it is insignificant, some momentum, which is finite, and some energy. The matter photon is hitting the matter electron. Again, it's a departure from classical physics. You are thinking an incident X-ray, which at the end of the day is an electromagnetic wave, is behaving like a stream of photons. What photons are doing? They are showing the property of material feature. What photons are doing? They are colliding with the electron. Okay, so they are actually colliding with the electron, and because of the collision is taking place, it was thought that the nature of collision is actually elastic here. Elastic collision takes place. So this was the idea. Just like that picture, you please see. See the picture, please. You see, photons are coming in, and ultimately it is hitting the electron, and if the electron is giving a bit of energy to the electron is moving. So kinetic energy of the electron also appearing from the incident photon because it was at rest. So photon loses its energy, and that loss of energy is indicated by the change in lambda. Okay. Now, as I mentioned, that Compton made two assumptions because he has to, even after the assumption that okay, incident X-ray is a stream of photons, and even after the assumption that there is electric collision between electron and photon, unless and until we do justify that wavelength is actually growing in the calculation, then all those things are discussions are meaningless. We actually, because Compton thought there is a collision going on, fine, between electron and photon, but the nature of collision is elastic. And he actually employed this idea of elastic collision for the measurement of the change in wavelength during the function, between the final wavelength of the X-ray and the incident X-ray of the X-ray wavelength of the X-ray. So now, if we apply both the conservation theorem, conservation of energy means energy before the collision and after the collision should be same, as I have written here, and conservation of, as I marked here, conservation of energy means this one, total energy before and after the collision is same, and this is the conservation of momentum. These two ideas we are now utilizing. You see how I am doing. Now, if you look at the picture, In the collision, how many parties are involved? Two parties are involved. One of them is photon, another one is electron. So it's a photon-electron collision. I mentioned the last day because you are making an elastic collision. If the initial energy of the photon is say Ei is equal to h nu, and after collision, the as I mentioned, electron which was at rest initially, so all its energy was rest energy. So now electron is also moving, making an angle some beta with the initial direction. Okay. So electron is acquiring its kinetic energy from the photon itself because photon losing energy because you see the value of the frequency is actually diminishing. So loss of energy of the photon will be appearing as the kinetic energy of the electron. If electron move, it should have some momentum, some energy. So keeping all these things in mind, the energy of electron, energy of photon, the momentum of electron, momentum of photon before and after the collision. Okay, we have to make a data table. So first we'll collect all the information related to energy conservation because you are now using that conservation of energy. If you look at the screen, you see, you notice energy of a single photon of uh, X-ray. I have is basically H nu. H nu is the energy before the collision. After the collision, if you don't understand, okay, before the collision, you can see here. Before the collision, energy was E is equal to h nu, and final energy is h nu prime. Electron was at rest initially, so it has got no kinetic energy. All its energy by the special theory of relativity will be m0 c square. Because relativity tells me, relativity, the prescription of special theory of relativity is that mass will vary because of motion. You can see there m0 by 2 power 1 minus v square by c square, but this variation of mass we cannot notice for daily life problem because that v by c ratio is very low and all these things I mentioned. So, but that theory of relativity tells that, or it gives that famous Einstein's mass energy relation is equal to mc square. The logic is that it tells us how mass of an object is connected with its energy. So, if the electron is static, its energy should be equal to m0 c square. Okay. Now, after collision, the electron is moving with the photon is moving with the energy h nu prime, and electron is moving with the energy mc square. And you see, by conservation of energy, total energy before the collision, which is h nu plus m0 c square, okay, will be equal to total energy after the collision, which is h2 prime plus mc square. Okay, that is the total energy. Now, if you look at the expression of momentum equation, total momentum before the collision was h nu by c. Okay, I have just shown you the calculation, and total momentum you can see here. Momentum is a vector quantity. If you look at the picture, look at the picture here. Suppose photons are moving around this arrowhead, that is h nu by. Photons are moving along this line. What I am trying to tell you now, the after collision, the photons are not moving along this line. Now I have to equate the photonic momentum before collision with the photonic momentum after the collision. So what I did the other day, now also same thing would happen, is that you see, if you look at the picture here, if you look at the picture here, this is moving in this direction, okay? You are supposed to move in the, not moving, it is making an angle, uh, this phi with the initial direction. So basically, the photons are moving along this arrowhead. They are not moving in the horizontal direction. But if you have to equate it with the initial momentum, and according to my drawing, this is phi. So this will be the cost, if this will be equated to the cost component of the initial move. So automatic question comes in, momentum therefore is getting divided into two parts. So perpendicular to the direction of motion also, one momentum component will come. But here no electrons are moving in that direction. So in that direction, momentum will be equal to 0. So before the collision, all the photons are moving with h nu by c momentum. So this is the direction of motion. In the direction of motion, momentum is h nu by c0. And the right hand side, uh, h nu prime by, you see, if you look at this, that is h nu prime, this is a theta, is a phi is the angle, h nu prime is theta. So I've shown the electron case, same thing with the, sorry, I've shown the electronic case. The, actually, this is the direction of the photon momentum. You see, photons are moving along this direction. You have to take the component in the direction of motion and perpendicular to the direction of motion. While the geometry of the problem, this is also theta. Okay, so basically it will become h nu prime or hf or the lambda, whatever you see, or you may say h nu prime by c cosine theta around this direction, and h nu prime by c sine theta perpendicular to this. Okay, so in the direction of motion, the photonic component is h nu by c, and but no photon moves perpendicular to the motion. Okay, so photonic momentum is 0 perpendicular to the incident. In the direction of incidence, photonic momentum is the first component, h nu prime cos alpha, perpendicular to incidence is sine component. Here I am choosing downward direction as plus sign. Similarly, if you do for electron, you see electron was at rest initially, so its momentum is 0. And actually, whatever I have drawn here, this is basically the momentum of the electron. If m is the mass of the electron according to this formula of relativity. So in the direction of motion, it is mu cos phi, and perpendicular to the motion, it is minus mu sin phi. Now, you will be getting two momentum conservation equations, therefore. One is the energy conservation, is already mentioned, summation of two parties are involved. So total energy of electron and photon before the collision is h nu uh, is plus m0 c square, and after the collision h nu prime plus m c square. Momentum also before the collision h nu by c, and after the collision that same component, and after the collision it is becoming the same component, is becoming the h nu prime cosine theta, because you have to take the component perpendicular direction, it is 0. So total momentum in the direction of, so if you write down the equation the of the momentum conservation now, you notice, so this is the momentum in the direction of motion, it is h nu by c plus 0. Okay, before the collision, after the collision, the cosine component of h nu prime plus mu cos phi perpendicular to the incidence, all at 0 because electron is at static and no photon moves perpendicular to the direction, and it is equal to h nu prime sine theta minus mu sin phi. So sir, we get the three equations. One is the conservation equation in energy, and two equation. One is the and two conservation equation in momentum. Now, if you exploit this three equation, you can actually calculate the change in wavelength taking place. I can show you also very simple calculations are there. So let me show you this calculation, okay, how it is coming. Okay, just a matter of 5-10 minutes. Wavelength lambda. Now this was the electron. This is the direction of incidence. Now what is happening? If I draw a line here, the left hand side of the picture is before the collision. After the collision, this is my photon. For example, it is making an angle phi with the initial direction. So if the initial frequency is nu, the nu prime is less than nu and wavelength is greater than lambda. And electron, which was initially at rest, it is making an angle theta with the initial direction, moving with a velocity u. Mass of the electron is m0 by root over 1 minus u square by c square, and momentum of the electron is ma, like this much. So now the conservation equation tells me for energy conservation I get this much. Okay, this was my table before and after the collision. Okay, the electronic energy is m0 c square and photonic energy is h nu. And after the collision, electronic energy is mc square and photonic energy is h nu prime. So these two are equal. And for momentum equation, momentum conservation, what you get is this much, that in the direction of incidence, along this direction, photonic momentum is h nu by c, perpendicular to incidence before the collision it is 0. And according to this description, all the photons are moving in this direction. So by geometry of the problem, this is also phi. So we get photonic momentum in this direction component h nu prime by c cos phi, and perpendicular to incidence h nu prime by c sin phi. And for so basically, in the direction of incidence, your photonic component is before the collision is h nu by c. Now electron is at rest before the collision, so plus 0, and h nu prime by c cos phi in the direction of incidence. Now come to the case of electron. Electron is moving along this direction with a velocity u. If you take the component, if it is phi theta, mu cos theta, and this is minus mu sin theta. So perpendicular to incidence, it is like no electrons are moving, no photons are moving. It is like h nu prime by c sin phi. This is the photonic part, and electronic part is minus mu sin theta, because if this is plus direction, it has to be the minus direction, like that much. So we get two equations from here on. So this equation is like h nu minus h nu prime. Okay, here there would be photonic mu cos theta. So from this, in the direction of incidence, my equation is like h nu by c plus 0, h nu prime by c cos phi plus mu cos theta. This is my equation. And perpendicular to incidence, it will be h nu prime sine phi is equal to mu c sine theta. So if you consider this as equation 2, this as equation 3, and this as equation 1, from equation 1 is the conservation of energy, equation 2 and 3 are conservation of momentum. You can write down from equation 2 and 3, if you take 2 square and 3 square and add them up, you can get one beautiful equation. Okay, that is h square nu square plus h square nu prime square cos square phi plus minus twice h square nu prime cos phi, and it will be h square nu prime square sine square phi, and right hand side will be m square u square c square. So this gives you an equation h square nu square plus h square nu prime square into sine square plus cos phi equal to 1. Twice h square nu prime cos phi equal to m square u square c square. So let me call this as equation 4. This is a conservation equation in momentum. This is taking a form like this. Okay. So momentum conservation is taking a form like this. So now from the energy conservation, from this equation, we can slightly write down this way, the conservation equation in energy. If we take the conservation equation in momentum, so from momentum conservation, we get this much, h square nu square plus h square nu prime square minus twice h square nu prime cos phi is equal to m square u square c square. And for equation in energy, that is h nu plus m0 c square prime plus m c square. So this gives you this much, h nu minus h nu prime plus m0 c square equal to mc square. If you square this equation, you get this much, h square nu square plus h square nu prime square twice h square nu prime plus m0 c square equal to m square c to the power 4. You'll get here m0 square c to the power 4 plus twice m0 c square h minus c prime. Now we'll replace this m square c to the power 4 with the help of this equation of mass variation. M equal to m0 square root of 1 minus u square by c square. U is the speed of the electron. So this will become m square equal to m0 square c square minus u square. This gives you m square c square minus m square u square equal to m0 square c square. So now you have to replace this quantity. This gives you m squared c square is equal to m0 squared c square plus m square u square. So if you multiply with c square, it will become m square c to the power 4, m0 square c to the power 4, m square u square c square. So you can replace this quantity by this formula, m0 square c to the power 4 plus m square u square c square. So basically these two will cancel each other and you get this equation, okay? And equation, you get this equation. We may call this as equation say 5. This is equation 5 and this is equation 4. Both the equation has got similar right hand side. If you compare both the equations, I can write down, okay, if you compare both the equation, left hand sides are also same. So what does it gives you? If you see compare left hand side, h square nu prime square minus 2i h square nu prime cos phi. This is coming from 4. And from the other equation I am getting this much. H square nu square plus h square nu prime square minus 2i h square nu prime, okay, plus 2i m0 c square h nu minus nu prime. Now this will cancel. So this will be taken to the other side. 2i h square nu prime into 1 minus cos phi and 2i m0 c square h nu minus nu prime. You can see from the equation 2 and 2 will cancel. One of the h will cancel. This nu can be taken to the other side, nu by nu prime. So this takes a form like this. 1 minus cos phi is equal to m0 c square. Nu prime means 1 by nu prime minus 1 by nu. If we get this c inside, this gives you this much. One h is leaving here. This gives you h by m0 c into 1 minus cos phi is equal to c by nu prime minus c by nu. Now c by nu prime is nothing but wavelength lambda prime, and c by nu is nothing but lambda. So this gives you lambda prime minus lambda equal to this much, h by m0 c into 1 minus cos phi. So this is the change in wavelength, okay, or delta lambda, the Compton shift. It's a long calculation, but not a difficult calculation. So therefore, if I look at the experiment of Compton effect, so this was the X-ray coming in of wavelength lambda, or photons coming in of energy say h nu, momentum h nu by c along this direction. This is one of the electron of the carbon atom. So after this is the scattered photon, wavelength lambda prime, frequency mu prime, and so on, mu prime less than mu. This is phi, and electron is moving, making an angle theta with the initial direction, with the speed u, with the mass m is equal to m0 by the power 1 minus u square by c square, and momentum of the electron is mu. Now this change in wavelength of the electron, of the photon, from lambda to lambda prime, I have calculated, which is now becoming like, as you can see, h by m naught c into 1 minus cos phi. Okay. Now what you have to show that this is a positive quantity, because wavelength is basically growing in the experiment. Okay. So now to realize this portion, now let me get back to the PowerPoint again. Okay, there I have already made discussion, some discussion. So please visit it, it will be easier for you to realize. Let's see here, okay. So these are the calculation I was talking about, wavelength shift have taken place. Now we have to show that it is greater than 0. Before that, you see, look at the expression change in wavelength into h by m0 c1 minus cos phi. In the drawing, actually, my calculation was phi is theta. It is written here according to this picture. That is the angle of scattering. Now, one thing you try to realize, okay, one thing you try to realize, you see, this quantity basically depends on the two things. Left hand side is wavelength, so it has got the dimension of length. Right hand side 1 minus cos theta. You see, cos theta varies from -1 to +1, so 1 minus cos theta varies from 0 to 2. And cos of something is always a number, so it has got it is no dimension. Now left hand side is an equation, so both sides should have same dimension. Left hand side already have the dimension of length, so right hand side must have the dimension of length. 1 minus cos theta has got no dimension, so h by f naught c must have the dimension of it must have the dimension of length. So that length is now henceforth we call as Compton wavelength. Okay, it should have the dimension of length. It is called Compton wavelength, which is a constant quantity like 0.0243 angstrom. Another important idea is that if we again look at the expression, so it is sometime we write down at points lambda c, the Compton wavelength, 1 minus cos theta. Now 1 minus cos theta, if you look at that expression, it will become 1 minus cos theta can vary from 0 to 2. It will become 0 when cos theta is 1. When cos theta will be 1 according to this drawing, when there is no scattering of. If no scattering means basically what is going to happen? No, in the electron is the X-ray is moving straight. Okay, no change in the it is moving straight. Okay, no scattering taking place. So no scattering means no wave change in movement. Like on the other hand, if cos theta is theta is other than 0, cos term is higher than higher than sorry. If theta is other than 0, what would happen? 1 minus cos theta, this quantity will be other than 0. Okay, and it can go up to positive +2. So it is never negative. So if there is some scattering, that means if some departure or some deviation from initial path, when that angle of scattering, as you can see in the picture, theta is non-zero, then 1 minus cos theta is always a greater than 0 quantity and can go up to 2. And h by m naught c is already a constant, as I mentioned. So that quantity lambda final minus lambda initial, the change in wavelength is a positive quantity. Okay. So this is the prescription. This is a positive quantity. So we expect that wavelength will actually increase in the experiment if there is a scattering. Now this is another peculiar discussion. The idea is that again get back to the calculation part. Okay. If we get back to the calculation part, we look here in this expression. Here in this expression, this actually this is there is the age already. This age by m0c is the Compton wavelength 1 minus cos of the angle of scattering. Here phi is the angle of scattering. Okay, in my drawing, and this is called angle of recoil. Just now I told you this change in wavelength or this lambda prime minus lambda. This is constant like 0.0243 angstrom, and 1 minus cos theta, if you look at this value, it can vary from 0 to 2. 0 to be when it will be 0 when phi is 0. Okay, so that means if there is phi is non-zero, 1 minus cos theta will be greater than 0. 1 minus cos phi. Okay, 1 minus cos phi will be greater than 0. So that is something that is I'm trying to tell you. Now you see, therefore you can see this phi can vary. This angular scattering can vary. And depending on the variation of phi, this 1 minus cos phi will vary, and depending on that, the wavelength change will also vary. So now let us discuss how this change in phi can influence or can control the change in delta lambda or wavelength change. Wavelength is going to change if phi is 0, a non-zero. That you came to know. So now we consider a few cases. Suppose the first case is obviously there is no scattering. Phi is 0. Phi 0 means, if you think in terms of picture, X-ray comes in and it moves straight forward. Okay, no scattering is taking place. So that means it is not facing any electron. If you calculate delta lambda, it is lambda c into 1 minus cos phi is 1. So there is no change in wavelength. Second case may be, suppose phi is equal to say 45 degree, pi by 4. So if I show you in the picture, it is coming. So this is your electron, and now wavelength change is taking place. And this is your angle. This is 45 degree. If you calculate delta lambda, lambda c into 1 minus 1 by root 2 cos 45 degree. So this is 1 by root 2 means 1 minus 0.7 kind of thing. So this is like 0.3 lambda c. 0.3 lambda c means is like 0.007 angstrom. So wavelength is change is taking place. Okay, delta lambda is basically, so for non-zero alpha, alpha greater than 0, delta lambda is becoming positive. It is growing. Now another option may be say alpha equal to say 90 degree. Sorry, phi is equal to 90 degree, pi by 2. If you choose phi is equal to the angle of scattering is equal to 90 degree, 90 degree means in this case it will move in this direction. So if you calculate delta lambda, it is basically 1 minus 0. So the change in wavelength is only 0.0243 angstrom. But the good news is that with the angle of rise in alpha, change in wavelength is also rising. Now, if I consider another case, so phi is equal to 9 pi. So the picture, if I draw it, you see, if phi is growing in this direction. Okay, along this line it was 0, now it has reached to 90, now it is approaching pi. Okay, so now I am talking about say phi is equal to pi. So if this is the electron, the idea is that it will not follow this path, rather it will bounce back, so that it makes the angle is equal to pi. So delta lambda, we will have lambda c into 1 plus 1, that is basically twice of lambda c. So this is basically 0.05 angstrom. So wavelength change will be the 0.05. Now you see you cannot go beyond this value of pi alpha phi is equal to the angle of scattering. Beyond this does not give you anything new because these angles are equal. So the maximum value of possible of change in the wavelength is pi, the 180 degree, and you can see here the change in wavelength is maximum 180 degree, and obviously the maximum shift in the wavelength is only sorry, by change in phi, the angle of scattering is maximum pi, so corresponding change in wavelength is 0.05 angstrom. So that means the wavelength change taking place in Compton effect study is maximum 0.05. So if you bring in it extra 1 angstrom, it can become 1.05. Okay, it will not become 500, okay, or 5,000. So change in wavelength is very small. So with this in mind, let me quickly answer two questions. That is why you are using X-ray and why you are using the light element in the experiment. Now the main mantra of explaining both the question is that this collision that you are seeing in Compton effect experiment is taking place between the incident photon maybe of energy h nu and with the electron of the metal with the electron of carbon atom. Now this is one of the free electrons of the carbon atom. So the main point is that why we have to answer these two questions. Why we are using a light element. Second question is that why you are using X-ray. Now to answer both the question, main point is that the collision you are taking place, you are seeing there, this electron is actually one of the free electrons of that particular atom. So whosoever is the photonic energy coming in, the first job of the photon energy, H nu, is to make the electron free by overcoming the Coulombic attraction of the nucleus, because every electron is attached to the atomic system by Coulombic attraction. If the atomic number is Z and electronic charge is E, here there is Z amount of charge. So a Coulomb force Z square by 4 pi epsilon 0 r square x. So considering r is the radius of the atom. Now, if you look at the expression, the atomic radius is of the order of 10 to the power minus 13 meter. So from atom to atom, what is going to vary? Z is going to vary. So if I consider the suppose Coulomb force in a element with high Z is equal to 92, which is for uranium, and if I compare this with a element of Z is equal to maybe uh, for carbon 6. If you compare here, Z is more. So where Z is more, Coulomb force is more, and where Z is less, Coulomb force is less. So in uranium, Coulombic attraction on the nucleus, on the electron is very high. It is always difficult to make free the electron in uranium because you need lot of energy to overcome the Coulombic attraction of this huge number of electrons. Okay, the huge the immense electron nuclear interaction. So basically, it might happen. You see, suppose you are sending photons here to make free the electron. Okay, it might happen. This feature might take place. Suppose this is the atomic system, and this is your electron. It is under Coulomb attraction. Question is that if this is a uranium atom, Coulomb force is very strong, and if this is a again this is electron, again it is under Coulomb force. If this is a carbon atom, Coulomb force is relatively weaker. So basically, what you are trying to do in Compton effect, suppose you are sending some radiation here, you are sending some radiation wavelength lambda. The idea is that all frequency energy h nu. The idea is that if h nu, this energy is sufficient to make, you see, you need lot of energy in case of uranium, and it can be done with much lesser energy in case of carbon. Another point is that, so basically what it does, that means if you have to make the electron free in uranium, you need lot of energy. So probability of making the electron free is much lesser in case of uranium because the atomic attraction is more. On the contrary, because of the incidence of external photons, the probability of making the electron free is much lesser because of the profound Coulombic because of the very less Coulombic attraction in case of carbon atom. So, okay, very less Coulombic attraction. So basically, it is easy to make the electron free in carbon atom. Okay, compared to it is very hard to make the electron free. So that's why it's because of this common sense. Okay, the carbon of you see always element of low atomic mass like carbons are used. And even if you use, say, for example, suppose still you are using heavy element, the heavy element like uranium. Then if you explore this definition of Compton wavelength or shift in a Compton wavelength, it tells you h by m naught c into 1 minus cosine of the say phi, the angle, the picture I was showing you. Now, if the collision, what is m0? M0 is a particle with which the incident radiation is making collision. It might happen with a heavy element, the attraction is very strong. So then we will assume that the photon coming in is actually colliding with the entire atom because it is not getting an electron free. If you do similar calculation, then m0 would be replaced by the atomic mass. Okay. So what it does, atomic mass, say suppose uranium, it's very high. So this atomic mass is much larger. Okay, because atomic mass Ma is too much high, and delta lambda will be too much small. So theoretically it might take place, but it may not be detected because maximum change in the delta lambda taking place is only 0.05 angstrom. Now another very important question that I should answer also, that is why you are using X-ray for the purpose of the experiment. Again, the mantra is that you have to, main objective is that you have to overcome the Coulombic attraction of that particular nucleus. If the atom is Z, atomic number is Z, keeping Z amount of charge, there is a very strong Coulomb force acting, depending or weak, whatever it may be, depending on the nature of the Coulomb forces, considering R is the atomic radius. Suppose you are sending photons now, so your objective is to make the electron free. Okay, so what is the job of the photon? The photonics job is to make the electron free, make free the electron. So how do you get it? You just judge the photonic energy. Okay. So we'll calculate this in case of visible light, and we'll calculate this in case of X radiation. If you calculate this in case of visible light, it is like this much. 6.62 10 to the power minus 34 joule second is the speed, and speed of light is like 3 into 10 to the power 8 meter per second. Suppose you are using visible light of say yellow color. For lambda yellow, if you use, it is like 6,000 angstrom. So 6,000 into 10 to the power minus 10 meter. So now therefore energy will be equal to 6.642 10 to the power minus 26. 6 into 10 to the power minus 7. Now it will be in joules. If we have to divide this in electron volts, if you divide it, get it in electron volt, divide this by 1.60 10 to the power minus 19 electron volt. So if you calculate it, its value will be close to 2 electron volts, because 10 to the power minus 7 and 19 will make it minus 26, so it will be like this. On the contrary, if you calculate the same thing for X-ray photon, suppose the wavelength of X-ray photon is 0.6 angstrom, because wavelength of range of X-ray is 1,000 times smaller, okay, or even in this case 10,000 times smaller. Okay, it is like H by lambda 6.62 10 to the power minus 34, 3 into 10 to the power 8, 6 into 10 to the power minus 11. You can see here, if we calculate it, 6.62 into 10 to the power minus 26 into 3 by 6 into 10 to the power minus 11. If you divide this by 1.602 into 10 to the power minus 19, then it will be electron volts. If you do so, you can realize on 10 to the power plus 4 will come. The rest of the story will be remaining same. So therefore, this is the energy of a single photon of X-ray, and this is the energy of a single photon of visible light. And you can see who is having more energy. Obviously, X-ray is having a lot of energy, 10 to the power 4 times more energy. So therefore, probability of, that's why X-ray is always preferred in the experiment of Compton effect. We get back to the picture. Same story. That is why X-rays are used, why carbon atoms are used, the elements of low atomic mass are used. So those questions I tried to answer by hand. Okay. Mantra is same in both the cases. It is a collision between incident photon and one of the free electron of that particular atom. Whether you can make the electron free or not. Okay, it depends on that. You can see there. So its probability of making the electron free is much higher with an element of low jet. So that's why carbon is preferred, and much larger with X-ray. So that's why X-ray is preferred. So now you have a long journey, okay, starting from Planck to photoelectric effect and now to Compton effect. So many discussions, so much of discussion. But you should never forget the main concept that is generated is the quantization of energy, and from photoelectric effect and Compton effect, they are also quantization of optical energy. They are called photons. So now we need to now actually revisit some of our further old concepts. For example, we will study uh, reflection, refraction in normal process. So how those things could be connected with our class now? Because today now we have got a new concept that radiation means or electromagnetic wave means like stream of photons. Uh, you already need also, but this is justified today, particularly by the both photoelectricity and Compton wave experiment. So after knowing this photonic nature, and we now need to compare with some of our older knowledge which we already have. Okay. So we'll do that, but you see what I've written there. You have to wait for the next class. Thank you. It has been a long journey. Thank you for your cooperation.
Like a bird on a tree, I'm just sitting here. I got time, it's clear to see. From up here, the world seems small. We can sit together. It's so beautiful, you and me. We meant to be in the great outdoors, forever free. Sometimes you need to go and take a step back to see the truth around you. From a distance you can tell. You and me were meant to be